So this time we're going to talk about document-level models. And I think this is one of the kind of interesting and maybe unsolved research areas in neural networks for NLP. I think we do a really good job at modeling medium-term context over one or two sentences, but still like generating coherent text across documents, understanding full documents and like the relationships between sentences is something that we definitely haven't done well yet. So what I'm going to talk about is kind of the state of the art in this area, but I'm not going to give you all the solutions, and hopefully you can come up with interesting solutions for some of the things here as well. So just as a very brief review, some NLP tasks that we've handled so far. We've handled language modeling, where you want to predict the probability of a sentence. We've also handled things like parsing, where you want to induce the hidden structure of the sentence. We've also handled things like classification. It doesn't necessarily need to be a tree, but you take in a sentence and you classify it into a class. And we've also handled things like entity tagging, named entity recognition. So the reason why why we put this here is we have some tasks over documents. So the first obvious one is document-level language modeling. So we have a document and we want to model its probability or its coherence at a multi-sentence level. This is most closely related to single-sentence language modeling, of course. Document classification, also related to sentence classification. And then the last two are going to be the main things that I'm going to talk about this time because they're very different. Entity coreference, so which entities correspond to each other. This is kind of a second step after we do NER. So after we figure out which things are entities, we want to know which ones correspond to each other. And then discourse parsing. So how do the segments of the document correspond to each other? And this wasn't included in the reading, so I'm going to try to explain it a little bit more carefully. So separating these, we have prediction of something using documents, and then we also have prediction of document structure itself. And I'm going to focus more on the second two because the first two are kind of like small modifications to the models that we've already covered for sentences. So for document-level language modeling, we want to predict the probability of words in the entire document. And obviously, sentences in a document don't exist in a vacuum. So we want to take advantage of this fact. So anecdotally, I'll cover that in a second. So of course, our go-to thing for language modeling is recurrent neural networks. And recurrent neural networks take in a word at a time, and they update our RNN state, and they predict the next word until we get to the end of the sentence. So a super simple method for language modeling is just to concatenate all of the words in the document as a big sentence and just pass your hidden state all the way through. So this is so simple, it's almost kind of a baseline that everybody uses for language modeling now. To give some evidence, if you train a language model on the Penn tree bank, sentence by sentence, you often get a perplexity of about 100. So perplexity higher is worse for language modeling. If you take the same model and you predict across sentences, you get a perplexity of about 70. So this is how big of an effect modeling document by document can have. This is a really big game. This is bigger than any method is going to give you. So just by passing information along in this particular way across sentences, you get a big gain in perplexity or modeling accuracy. So the reason why this is the case is simply because you can predict the beginning of the sentence more easily because sentences tend to flow in a particular way. So you know the beginning of the sentence. For example, if you have a sentence, "I hate this movie," then "but" would be a pretty good start for the second part of the sentence. So of course, if this was the only way to do things, this would be boring and this class would end very quickly. And the reason why this is insufficient is basically because if you if you try to model your long-term dependencies and your short-term dependencies in the same framework, you tend to miss out on modeling your extremely long-term dependencies. And I don't have any empirical evidence for this, but kind of you can think of an intuitive reason why, based on the features of neural networks. So basically neural networks, they have this highly discontinuous optimization surface, right? And it's very easy for them to fall into local minima. And one of the local minima that you could think of this falling into is something where it relies solely on short-term context to predict the next word. And because short-term context is much more predictive than long-term context, it first learns to predict using short-term context, and it doesn't have enough, it fits to that on the training data, and it doesn't have enough capacity or motivation to learn long-term context. So this, as I said, this is just my intuitive hand-wavy motivation for this, but I have a pretty good sense of how neural networks work by now, and it seems to make sense to me. So it'd be nice if somebody could go and prove that, for example. So there's lots of other attempts that basically try to make it easier to utilize long-term context in language models. And if you make it easier for the model to utilize long-term context, then it will be more effective at learning it. It won't overfit to using only short-term context at first. So basically the idea here, this figure is from Mikolov and Zweig, who did this in 2012. And basically what they do is they have some other function that calculates your long-term context, f of t, and then you feed it in either into the recurrent neural network layer, or you feed it in directly to the softmax when making your predictions. So this is kind of the standard go-to way of doing this, and there are small variations, of course. So then the question becomes, what context do you incorporate? And the answer, there's lots of answers for this. One answer is using topic modeling. So I think I've asked this before, I'm sorry, but how many people are familiar with topic models? It was most of the class, right? So the basic idea of, I asked how many people are familiar, and then everybody raised their hand and said how many people could implement it, and then everybody dropped it. So now topic modeling, just in a nutshell, basically is a non-neural method, usually done through sampling or variational inference, that allows you to assign words to topics. And it also, given all the words that you've seen so far, it allows you to assign a topic distribution to the document. So this basically gives you a distribution over all of the topics in the document. Maybe you have 50 topics. And then this is just a vector that you can stick into your softmax or something else. So this is a model that's not trained end-to-end. You pre-train the topic model and input it, and this worked pretty well at the time. There are also methods that you can do to train things end-to-end. So you use a bag of words of the previous, you use bags of words of the previous sentence. So the previous sentence, you have your sentence here, and you have like the dog barked. And then you have the cat ran. Actually, this is not a very good ordering. It should probably be the dog barked, but not the cat ran. But then you have basically a vector where all of the words that were present in the previous sentence are ones, and all the others are zeros. And then you embed this vector, and then you use this as additional information. So the idea here is that you don't need a separate topic model to learn the topic of the previous sentence. You can just embed the words, and that does a pretty good job of discovering that for you. You can also have this bag of words over not just the previous sentence, but also the other sentences, and feed this into a recurrent neural network. And that way you can keep track of the topic kind of flowing over the sentence. And you can also add attention, because you can add attention to everything. Another thing that people have done I don't believe these two works compared to each other. They seem to be doing kind of the same thing, but if you just take the last state of the previous sentence and you don't initialize the first state of your current sentence, but instead you feed the last state of the previous sentence into every time step of the next sentence, then this works better than just initializing the first state. So there's a bunch of options. Basically, if you're interested in doing this, you can look up any of these options and incorporate it into your model. They're all relatively easy. So this is what some easy tricks that you can do if you want to do document level language modeling. Are there any questions so far? There's a couple more complicated ones that I'm going to talk about later, but these are the ones that I have now. Okay, so how do you evaluate document language models or document coherence models? So there's been a lot of ways proposed to evaluate document models of document coherence. The easiest one is just perplexity, and this is present in most document level language modeling work. In my opinion, this is probably enough to, if you want to create a language model, perplexity is a pretty good way to evaluate it, but there are also a couple other ways. One very popular way is sentence scrambling. So the idea behind this model is, or this evaluation method is basically you take two sentences within the document and you swap their order. So you want to be able to see whether your model is accurately capturing the transitions between sentences. So if your model is able to identify the unscrambled one is better, then you get a higher score. The problem is these original data sets. These original data sets are really easy. So now modern models can get 99.7 accuracy about unscrambling sentences. So there's also a harder data set on abstracts, like scientific paper abstracts. That's a little bit more difficult than this. So unfortunately, I forgot to put this in the review. But if you have a question about this, I can send it to you. Another interesting one that people have taken a look at is a thing where they had crowd workers look at simple stories, and you read through the simple story, and then you have one of two endings, and you need to pick which of the endings is correct. And then another one is final word prediction. So you have a long passage. And you need to pick the final word here from this passage. So yeah, you have lots of options for doing these. I think I'm going to talk a little bit later about some caveats about this. Actually, maybe I'm not. So. In case I don't have the slide later, one caveat about the middle one, and maybe the latter one as well, is this was created using crowd workers, and they basically asked crowd workers to write a story, then they asked them to write like confusion sentences, and because they asked the people to write confusion sentences, there's small differences between the story and the real story sentences and the confusion sentences. So there's a paper called "Pay Attention to the Ending," which basically throws out the entire document and just classifies the sentences, and it gets 72% accuracy. And then their model that looks at the context gets like 73% accuracy, or something like this. So this is this common thread that has been becoming more and more obvious with these kind of crowdsourced data sets, which is you create this really nice data set that has context, and then based on the context, you want to make some prediction of a sentence. Other examples of this include natural language inference. So trying to pick entailment or contradiction or neutral. You throw out the entire input sentence and just try to classify so NLI has a hypothesis, a premise, and a hypothesis. So you throw out the premise sentence and just use the hypothesis sentence. I think this is the order. And even though you've completely lost the relationship between the two, contradiction sentences tend to have not more. So you get a high classification accuracy. So you should be relatively careful about these crowdsourced data sets and whether they're testing what you actually think they're testing or some sort of artifact. So this is the reason why I say you should just do perplexity. It's impossible to game perplexity, but yet people make lots of data sets. So. Okay, let me be more clear. So I think these data sets are good. I think data sets with focused evaluations are good, but I think it's very hard to create them right. So perplexity is still a pretty good measure. Let me take that back and make sure that I'm not discounting these data sets. Okay. So are there any questions so far? I'm going to talk a little bit more about language modeling as I talk about coreference and other things as well. Okay, so let me talk about coreference next. Coreference is interesting. Coreference and discourse parsing are interesting because these are methods that we're still really, really bad at, actually. We're still really bad at coreference, really bad at discourse parsing. So I think despite the fact that people have tried really hard and come up with nice methods, there's still a lot of work to be done here. So if you're interested in hard problems, these are good things to think about. So coreference, as you read in the reading, is basically you take noun phrases. Oops. Actually, I should put noun phrase coreference, not entity coreference. I'm sorry. So you look at noun phrases, and these can be stuff like a viable monarch, a renowned speech therapist, etc. And you try to cluster them together from the same underlying word. So just to do a very brief review of essentially what was written in the reading, the first thing you do is mention detection. So we have something like this, where we look up a renowned speech therapist. And what this example is trying to show is a renowned speech therapist is the correct mention. A renowned speech is not a correct mention. Despite the fact that if you say Abraham Lincoln gave a renowned speech at Gettysburg, then that would be a correct mention because so it's not super clear where these mentions occur. So even detecting the mentions can be difficult. So once you have the mentions detected, then coreference is basically clustering mentions together into equivalence groups. And detecting these mentions is a difficult and important step. And knowing the correct noun phrases affects the results a large amount. So you can attribute a large amount of this drop, of the drop in accuracy in coreference to noun phrase detection accuracy. So this is normally done as a pre-processing step, not jointly with entity coreference, but there are recently models that do both of them, or specifically one successful model that does them end-to-end. So the components, like any traditional machine learning model, we want to know the instances that we want to classify. We want to design the features of each of these instances. We have evaluation metrics that we would like to improve, and then we have a search algorithm for structure. So the search algorithm that they use, there's kind of two ones. I say covered in a later lecture, but I think I'll cover it briefly here as well. So for our instances, coreference is a structured prediction problem. So we have structures. Maybe I'll pop up the example. So we have for example, a text that has Hillary Clinton was the presidential candidate in the 2016 election. Clinton won some percent of the vote. She did something, and then you have Bill Clinton. If you want to know whether Bill Clinton corresponds to any of these entities or all of these entities, etc. And obviously, there are an exponential number of the ways you can do this. You need to partition these into groups, and partitions are exponential in number. So the two kind of ways that people do this is mention-based and entity-based. And the important thing here is if you look at Bill Clinton and Clinton, there's a pretty high chance that these would be linked together, right? So if you're just looking at mentions which mentions correspond to each other, Bill Clinton and Clinton looks pretty good. But if you know that she and Clinton and Hillary Clinton are all part of the same entity, then Bill Clinton and Hillary Clinton would probably not be the same person. So then it becomes easier to classify these. So the difference between mention-based and entity-based things is entity-based things treat clusters as things that you want to be classifying over, whereas mention-based methods treat mention pairs as things you want to be classifying over. So to give a more concrete example, between every two mentions, we want to classify whether they correspond. So Queen Elizabeth and her correspond to each other, whereas Queen Elizabeth and husband and King George and a viable monarch do not correspond to each other. So this has problems in that it results in yeah, actually, I'm sorry. I didn't make this slide, and I don't know exactly what it means by conflicts and transitivity. So if you really want to know that, I can check on it. But the more important ones in my mind are it cannot capture the entity in cluster level features. So and there's no ranking of the instances. So the most important thing here is, for example, if you have her, if you have things like her and husband, it's very clear that these things do not correspond to each other because her is a female, indicates female, and husband indicates male. And the mention pair models, well, they'll be able to say that her and husband do not correspond to each other. They won't, by a few leaps of inference, be able to say that the thing that corresponds to her and the thing that corresponds to husband do not correspond to each other. So it makes handling these things difficult. Then there's also entity mention models. So the idea of an entity mention model is basically you create a link between an instance or between a mention and a previous cluster that you've already done. So in this case, you would assume that Hillary Clinton, Clinton, and she have become a cluster, and you would want to decide whether Bill Clinton corresponds to that or it doesn't correspond to anything else. And this has the advantage of being able to do cluster level features. The difficulty here is that you can't do ranking between the antecedents, and cluster level features are still difficult to decide. And then finally, entity-centric models, basically you calculate some connection between the clusters, and you kind of group them up in an agglomerative clustering method. I'll be talking about those in a little bit. To make things a little bit easier, you can also formulate this as a ranking problem. So the idea is you know all the mentions that you've seen before, and based on this, you want to decide whether one of the mentions that you've seen before corresponds to this particular entity, or whether it's a new entity. So you do a ranking over the previous mentions, and if any of the previous mentions basically gets a score better than the false, better than new, then you group it together with that entity. Otherwise, you create a new entity group, basically. And for entity ranking, basically you have clusters for the previous mentions, and then you want to rank which of the clusters is the one that is which of the clusters is the one that correctly corresponds to this mention. So this is kind of a review. One important thing here is that up until this point, there were these extremely complicated sets of features. So for example, pronoun features, whether it's a pronoun, the number, the gender, the animacy, combination features, etc. And of course, as the common theme of this class, neural networks allow us to get many of these features without explicitly encoding them in feature templates like the one you saw before. So there's a few big advantages. One is that these allow you to learn the features with embeddings. So many, obviously embeddings tell us about whether words are similar or not, and being similar or not is a very strong indicator of whether things should co-refer to each other. Another thing is that many of the entity-based methods allow you to train directly towards the metric that you're interested in optimizing. And this is usually a good thing. I'll explain about this in a little bit. And another thing is that they allow you to jointly perform entity mention detection and clustering. So this is really, really useful and has proven to give you very good results for this test. And I'll cover all of these. So the first model I'm going to cover, this was by Clark and Manning in 2015, is Coreference Resolution with entity-level distributed representations. So this is a mention pair and cluster pair model. And each of these basically allow you to represent entities. They also, because the co-reference data is pretty small, they actually had to manually create a set of features as well, which include, it might pop up on the slide in a moment, in which case I'll talk about it. If not, I'll talk about it without the slide. But then the mention pair, they have the mention pair model, which is then used to determine between cluster pairs. And they have a couple, they have training objectives, including max margin training objectives. And then they have a cluster merging method that uses a policy network, and it's trained with a learning to search method. So let me, all of my slides have disappeared. Okay. Okay. So sorry. Here we go. Okay. So the method that they used here. Sorry, my animation broke my slides for some reason, but I'll explain without animation. So the interesting thing here is we need to partition things into clusters. So let's say you're not interested in entity co-reference at all. You might still be interested in clustering things together and doing a supervised clustering of things in clusters. So the method that they used here is actually pretty interesting for doing this. So you have A, B, C, D, E, F. And let's say A and B are in a cluster together, and then C, D, E are in a cluster together. So what you want to do is you want to be able to find this. So they have a mentioned pair model, and what the mentioned pair model is a model that calculates the similarity between each mention and each other mention in the document that you're working with. So they also have embeddings for each of the words in this. If I remember correctly, they sum together the embeddings for all of the words in the entity. So this is a very rough approximation of an entity, but that's what they do. And then they also have a few discrete features, like what is the relative position? Are they close together or far apart, etc. So then they take this, they run this through 2 layers of a feed-forward neural network, and then they get a representation of this. And then based on this representation of this, they classify whether these things correspond to each other or not with a max margin objective. So that's good. Then you can determine which of these entities correspond to each other, which of these entities do not correspond to each other. But the problem is, eventually we want to make clusters. So the way they do this is with an easiest first algorithm. So the easiest first algorithm, basically what this means is we calculate all the similarities between all of the entities and say, let's say the similarity between A and B is 5, the similarity between C and D is 6, and the similarity between all the others is lower than that. So then they merge C and D into a cluster, and you get the CD cluster. And then you similarly calculate the distances between them. You get 3, then you cluster this, and then you cluster this, and then maybe all your other values are negative, and then you're done. So it's basically you find the 2 things that are closest together, and you cluster them up together. So this is pretty straightforward, but how do you compare C and D, the cluster CD to E? And the idea is basically you have your mention pair model that is able to compare all of the mentions, all of the mention pairs in the document. And what you do is you simply take the representations learned by this mention pair model, and then you do max pooling over them. So the idea behind this is you look at all the comparisons, and you basically find it's very similar to finding the cluster or the entity in the cluster that's closest, or that has the most active of these similarity features. So I think this model really makes a lot of sense and might be useful for other clustering algorithms that you're interested in. As an auxiliary advantage, you can batch together this mention pair calculation and just do it between all pairs at first. And then when you do a merge, then you would just have to do this this cluster pair max pooling operation over the representations that you've already calculated. So I think this is a pretty good recipe for doing things. This is trained using a learning to search algorithm. I talked a little bit about learning to search, but basically the idea is you merge things together. You take your model, you make a decision based on your model, you merge things together, and then based on this, you try to train your model to take the optimal decision given all the previous model decisions. So it's kind of like the max margin objective where that I talked about, where you step through your sentence and you make decisions, and then you try to make the optimal decision next based on the decisions that you've already made. So now that I've explained this, I can like the other ones are relatively easy. But are there any questions about this? Yeah.
Yeah, a lot of the collaborative approaches want you to specify beforehand how many clusters to make.
Yeah.
How do you handle that in situations?
So in this particular situation, what they did is they have a score for each mention pair, and their like do not cluster anymore score is 0. So anytime something's less than all of the remaining clusters are less than 0, then it just cuts off. And of course, they train their model to do that, so it basically learns to pick the number of clusters as it goes along. Any other questions? Okay. So I'll move on to the next one. So the next one is a method that, that uses, the title says deep reinforcement learning. The method that actually worked the best was not what I would call a reinforcement learning model, but basically it's a continuation of the previous model. So the previous model, what they did was every time they would merge something together, and then they would pick the next best action based on the things that they had already done. So it was a really simple model of choosing your kind of oracle action for what you wanted to do next, for what action you wanted to choose next. However, as you noted maybe very briefly in the reading, there are co-ref evaluation metrics, and you want to specifically optimize for this co-reference evaluation metric like cluster purity or B3 or the MOOC evaluation metric. So they have the same features and structure, but they changed the objective. And they basically choose which which clustering decision you make is the action of the agent. And the final reward was one of the four main evaluation metrics in coreference B cubed. And so what they did is they had a standard reinforce method. They had a standard reinforce method where basically they rolled out all the way to the end of the, they did all of their clustering decisions. I think most people remember reinforce, but in case you don't, you have your reward of your output y, and then you multiply the negative log probability of y given x. And this is kind of the function that you use to optimize. So the simplest thing you can do is you can make all your co-reference decisions, calculate your B cubed, and then scale your maximum likelihood objective according to this B cubed measure. But actually, what they found worked much better than this was a reward rescaled max margin method. Actually, reinforcement method's probably wrong. It's a max margin method. So what they did instead was they did a merging decision, and when they did their merging decision, each merging decision they checked how much the optimal B cubed would decrease based on this decision. So they basically calculated the best possible B cubed they could get given all the decisions they've made so far, and they made the margin equal to the decrease in that optimal thing. So this is one very good example of something where you can use your knowledge of the optimization metric, the metric that you want to use, to give reward at every time step, as opposed to only getting reward at the end. And that's why this method worked significantly better for them. So basically, yeah, are there any questions about this so far? No? Okay. So I'll move on to the next one. This is basically a pretty simple, modification, I guess. It's kind of the research was done at the same time, so it's not really fair to say it's modification, but fitting this idea in the previous framework is very easy. Basically, the idea is here they learned cluster level features according to the by just pooling together the pair features. And instead of doing that, they learned the cluster level features by running an RNN over the entities in the clusters. So based on this, they have some nice analysis about what clusters they found. But the idea is pretty simple and could fit in a number of frameworks that use these cluster features. So now maybe the most exciting one of all of these is up until this point, including in the reading that you saw, it was very, very common to pick your noun phrases before doing co-reference. So the big contribution of this paper is that actually they jointly pick which noun phrases you want to be using and do co-reference at the same time. And I think this is good if this method would work for other things where you want like spans of things that you're interested in as well. But the main contribution of the paper is kind of twofold. One is, can you represent all the features in a more typical neural network embedding? And also, can the neural network allow the errors to flow end to end? So this solves span errors, which were things that were not handled by many previous things. So the model is actually quite simple. And the way it works is they run a bidirectional LSTM over the entire sentence and document. And for each span, they take the left vectors of the bidirectional LSTM, the right vectors of the bidirectional LSTM, and then also an intentional sum of all of the words in the span. So on the left side, you get kind of you get the entity read backwards along with all of its right context. On the right side, you get the entity read forwards along with all of its left context. And then the attentional sum lets you focus on the more important words in that. So the way the model actually works is something like this. So for each span, they have a score that allows you to. So for each span, you have a score that basically says this looks like a span. This is simple, right? So you just take in the span representation and you predict a score. And if that score is high, then it looks like something that should be an entity or a noun phrase. If that score is low, it looks like something that should not be a noun phrase. Then when they calculate the next thing they do is they calculate the score of the mentioned pair. So you have your previous mention, your antecedent. You have your score, and you calculate basically the probability that. In this example, you have General Electric, the Postal Service, and the company. You calculate the probability that the company corresponds to General Electric. You have the probability or the score that it corresponds to the Postal Service. And then you also have a dummy, which basically always gets a score of 0. And then you decide based on this. So the way this works basically is first they extract all of the candidate entities. Then they extract all of the based on this they extract all of the corresponding. They extract all of the pairs, and then they basically step through and rank the pairs. The inference model that they use is kind of tricky. The reason why this is not super straightforward is you could have the Postal Service and you could also have Postal Service. And basically they have this greedy thing where you go from the top of the probability of the entity mentions, and the top of the probability of that each noun phrase is an entity, and you step through, you select it. So if the Postal Service gets selected, then you just delete Postal Service as a candidate. And the whole thing is trained using maximum likelihood. They have this, one problem with this is that if you actually took all of the spans and considered all of the spans when running your coreference model, you would just have this extremely large number of spans that you could never handle. So in order to handle this problem, they basically prune the spans, so you only consider spans with a reasonably high probability of being actual mentions. So, and this is at training time and testing time, yeah.
Could you explain more on the pruning? So, how does it work on every training instances? Do you keep pruning based on some length, or is there a fixed size span?
Oh, it's based on the score. So the mention rank, or the mention ranking model. If you call it a mention ranking model, basically what it's doing is it's saying this is likely to be a mention, this is not likely to be a mention. So you prune everything with a score that's below a certain threshold for being likely to be a mention. And only with respect to those do you actually calculate the pairwise scores. So it's relatively simple to calculate the probability that it's going to be a mention, but if you have to do all pairs of that over your entire document, then that's n squared in the number of spans instead of just n in the number of spans. So I guess it would be n to the fourth in the length of the document, which would not be feasible.
But even with the pruning, it's an end-to-end trainable model.
Even with the pruning, it's end-to-end trainable, so they're not pruning everything. They're pruning just some of them. Okay. So this, I think now with this method, the score for coreference, the b cubed score, is about 69. So that's starting to get reasonably good, but there's still lots and lots of errors in coreference. So that's the reason why I was saying this is certainly not solved yet. So like all analysis tasks, one of the questions might be why should I care? I have bi-LSTMs and they work, so why do I need coreference? The LSTM will just learn it for me. But there is quite a bit of evidence that coreference can actually help in these models. And the reason why is precisely because document-based models, having a little bit of bias about the way they pass information along the document can help a lot in modeling. So one example is language models. There's a few papers on language modeling with coreference. This is only one example of them. But basically the idea is that every time you have a coreference link, you pass information along that coreference link directly to the state as opposed to using it. There's also methods for coreference-aware QA models, and this is basically your encoder passes stuff along. This was done by Buan Dingra in NLP. Finally, there's discourse parsing. So discourse parsing, this is like the parallel of syntactic or semantic parsing, dependency parsing for discourse. So an example is the projections are in the neighborhood of 50 cents a share to 75 cents, compared with a restated 165 a share a year earlier, and then circumstances when profit was, etc. So you can see that you're making a comparison between the 50 to 75 cents versus 1.65 cents, $1.65. And you're also elaborating on the circumstance in which this information held. So, and this is done on the level of something called an elementary discourse unit. So it's not necessarily sentence by sentence. It's actually kind of clause by clause. So yeah, discourse parsing is basically parsing a document into this structure. It looks like a phrase structure tree or a dependency tree, depending on how you express it. And there's a number of neural models to do this. The reason why neural models are really good at this, as you probably can imagine, is because this is a really hard problem if you don't have some sort of way to represent sentences. In neural models, you can run some sort of feature extractor over the sentence and extract kind of the gist of the sentence. Of course, there were methods before neural models, but neural models have been relatively effective at this. So a first example is a shift-reduced parser with features from 2 stack elements and a queue element. So this is basically just a regular shift-reduced parser, like the ones I talked about in the tree, in the syntactic parsing thing. It's using a feed-forward neural network, not something like a stack LSTM, and it's just taking the 2 stack elements and the queue element and extracting features from them. In this case, they're extracting discrete features, including like what is the head, what is the what is the head of the phrase, what are the left and right words, etc., and various things, and they're projecting them into a distributed space for better generalization. And they have a bunch of different ways to do it, but in the end, basically they extracted features from the stack, features from the stack, features from the queue, and just did a fully connected layer to project this before making their classification choice. So this actually worked really well. It still basically beats out the more complicated models. In there's kind of 3 ways that discourse parsers are evaluated, and kind of the most important one maybe is relation accuracy, which is the accuracy between of the relation links. And this one still is very competitive there. There are more complicated models, like recursive neural networks for discourse parsing. Basically, the way it works is you have 2 representations over sentences, which are acquired using whatever method you want. And then you decide whether these 2 should be merged or not by taking a pairwise score, inputting these 2 vectors, and predicting a score. And then once you've done that, you predict the relation. So basically, the relation prediction is separate from this. And then they have kind of a bottom-up merging operation where they do this, and you can search over these merging operations as well. If you want to get a little bit more complicated, there's this model. So it takes a bi-LSTM to encode each of the elementary discourse units. Because each span in the discourse tree corresponds to multiple elementary discourse units, you also have another bi-LSTM on top of that. You concatenate these together, and you have a tensor-based transformation of this into a new space. And then you classify the span, you classify the nucleus, and you classify the relation. So it's just a slightly more sophisticated model for this. Oh, and and actually you have attention on this as well. So long story short, basically the main difference between this and a regular parsing model is that you need something on the bottom to turn your elementary discourse units into vectors. And then once you do that, it's more or less the same thing. The same thing as regular parsing. So you can apply a regular parsing model. So one of the interesting things about discourse is actually discourse is relatively easy when you have or deciding discourse relations is relatively easy when you have an explicit indication of the discourse relation. So like compared to is a very obvious one. When is a very obvious one. In many cases, though, you don't necessarily have this. So implicit discourse relations are not explicitly marked, but we would like to detect them when they are. So the idea behind this method, it's really clever. I think it's maybe one of the more clever uses of adversarial methods in NLP, simply because it's really appropriate for this problem. And the idea here is you want to classify relations, and you have an example of never mind and because you know the answer. So these are 2 EDUs. because is a very obvious discourse connective, so you kind of know that it should be there. You know what the relation should be because that's there. But if you don't have this discourse connective and you have just never mind, you know the answer, it's still because. It still means because, but it's just not explicitly marked. So what they do is they remove these explicit connectives from their training examples, but then they train something with an adversarial objective where you get the where if you get the representations from the one with and without the explicit connective, you get the same a representation that basically can't be distinguished from the other one. So I think this is also really cool because you can create nearly infinite amounts of training data for this, right? You can look for all the things with explicit discourse connectives and then just delete them. And you could train with this discriminator, even if you didn't necessarily know whether whether it was the same or not. So are there any questions about discourse parsing? So another thing I should mention is discourse parsing on the relation level is still really bad. As I mentioned before, it's about 62% accuracy. So this is another thing where if you want hard problems to solve, it would be a good one to consider working on. So there are uses of discourse structure in neural models as well. This is actually a recent paper, and I think it's a very nice paper. It's discourse structured classification with neural models, and what they do is they have kind of a discourse dependency structure where you have elaboration or a continuation or exposition or something like that. I forget what it was. Explanation. Expansion. Hiro, what was EXP again?
I think it's
Explanation.
explanation.
Okay, explanation. There we go. So you have these discourse connectives, this discourse structure tree, and basically they get the representation of a phrase by taking this the representation of its child phrases and multiplying it by a matrix that follows that's parameterized for each discourse relation. So this is actually. And then they also have an attention over each of these. So it's not attention that adds up to one over all children. It's actually 0 to 1 for all of these children here. And based on this, they get the new representation of the phrase. So they compare this to a bunch of other models, and I think on 4 of the 5 data sets they run, they do very well for document classification. And I think this is nice because it shows that this is useful for across documents. But my favorite part of this paper is this graph. So what this graph is showing is this is your F measure on the RST tree bank. So this is your discourse parsing accuracy, and this is your document classification accuracy. And you can see there's this kind of linear increase in document classification accuracy as you improve your discourse parsing accuracy. So what they did is they basically made their discourse parser weaker by training on only a subset of the data for the tree bank, and then ran based on this. And you can see that despite the fact that discourse parsing accuracy is only at 62%, they're still beating the state of the art on this data set. And hey, it's only 62. If you extrapolate to 100% discourse parsing accuracy, you're suddenly beating the state of the art by 5 points or something like that, which is pretty convincing that this might be an interesting problem to work on. So even if you don't care about discourse at all, I hope the one thing that was useful this time is this graph. So then you can go back and take your own analysis tools and hobble them by training on only part of the data, and try to draw something like this that shows the importance of analysis accuracy in your linguistically motivated models. So yeah, that's all I have for today. Are there any questions about things? Yeah.
Just for the previous
Yeah.
So that graph that there is, so does that imply that like improved discourse causes accuracy is more, or like the general correlation causation thing, or is this just a general correlation?
Well, I think they controlled all the other covariates. I don't know what else could cause this. Yeah.
How did they convert? I mean, how did they get the classifier given the discourse parser?
How did they
Get the classifier given the discourse parser.
Oh, so what they do is they run the discourse parser on their training data. Then they train on the training data with the discourse parser, with the discourse parse training data, and then they run the discourse parser on the test data and also classify according to the discourse. Any other questions? Nope. Okay, thanks a lot. I'll finish up.